So I think it's time to start now. Hello everyone and welcome to OPA 5th online internship. This is our first live session of our series in production technology.
I think it's time to start now. Hello everyone and welcome.
Titled Production Optimization Using Nodal Analysis, presented by our instructor engineer Ahmed Salah, who has a bachelor in petroleum engineering from SOAS University. He is a petroleum engineer with 10 years of experience in oil and gas fields in Agipa Petroleum Company. He has a proven track record in optimizing artificial lift systems, completion design strategies, and well intervention operations for efficient production enhancement. So I hope you enjoy this session, and now it's time for Engineer Ahmed to start his presentation. Engineer Ahmed, the mic is yours.
Hello, everyone. Good morning, good afternoon, wherever you are. Good evening. I am Ahmed Salah, as Engineer Adil said. I'm Ahmed Salah, petroleum engineer in Agiba Petroleum Company. Today, we'll start with our first session of production technology, which is production optimization using nodal analysis. But first, I need to make sure that my voice is clear to all of you.
It's clear, Engineer Ahmed.
Okay, thank you. Before starting with production optimization using nodal analysis, in which we will use mainly software Prosper, we need to highlight that there is some prerequisites or that is must be known before we go deep into the well modeling. The requirement include fluid properties, include technical concepts regarding inflow performance and vertical lift performance. We will review these technical requirements before we begin our well model in Prosper. Okay, so let's start with our agenda today. So we'll introduce the concept of production system, the concept of inflow performance relationship, and vertical lift performance. What is meant by nodal analysis, and continue to our Prosper model. We'll begin the model with how to build our well model. Check whether this well can produce naturally or at which data it can produce naturally. Then we'll go to PVT matching, and also we'll come at the end whether we need to consider an artificial lift system or not in this well model. So it will be a basic well model, but we'll try to catch all the data or the input data or the power of Prosper as a worldwide known software for well modeling. Okay, so let's start with fluid properties. The main fluid properties we need to know is density. Density is mass per unit volume. Bubble point pressure for the fluids. Bubble point pressure is the pressure at which the natural gas begin to come out. Solution gas oil ratio. This is the main data that we need to include into the model of Prosper. Solution gas oil ratio is the amount of gas dissolved in the oil. So at the reservoir level, oil has some gas dissolved inside it. As oil go up inside the well bore, gas come out. So the solution gas oil ratio is the amount of gas that is dissolved at the pressure above the bubble point pressure, which we described earlier. The reservoir is said to be under saturated reservoir. But if the reservoir pressure down is below the bubble point pressure, then we call it saturated reservoir. And this is one of the selections that is mandatory during the building the well model to understand this concept. This is a basic concept for all petroleum engineers. Also, formation volume factor is a figure to know how much volatile is oil. Is the volume of stock tank condition, which means at surface, to the volume of oil at elevated pressure and temperature. Specific gravity is relative density of the liquid to the density of a given reference, which is water for us. So specific gravity for pure water is 1. We sometimes use this average specific gravity for the liquid to consider the specific gravity of water, which is saline water downhole, to the specific gravity of oil. So we use this formula to calculate the cumulative or average specific gravity for the liquid coming up inside the wellbore. API gravity is a measure of how heavy or light the liquid is compared to water. This is one of the inputs that we use that is mandatory to build our well model in Prosper. Also, sometimes this data is not available because to get all these fluid properties, we need to do some PVT analysis, some PVT sampling. We take the whole sample from the well and we take this sample to the lab and they make a lot of analysis, flash calculation, differential, a lot of analysis to get these numbers. But mainly this data is not available at all times. So we use offset data by analogy. So in case that we produce the development well that we produce from a field to a well-known field, we can use offset data. But if in other cases, which we had exploratory wells, and we don't have this data, we had to do some lab test study to get these fluid properties. Another concept that is mandatory for us is the pressure gradient or how to get the pressure at depth. This is the main formula that we usually use to get the hydrostatic pressure at depth, which is the pressure gradient of pure water to the specific gravity, which is relative density to the relative density of the fluid to the water multiplied by the vertical height. This is how to get the pressure at depth. Also, we had we need to understand some basic principles of oil production, which is reservoir drive mechanism. Reservoir drive mechanism first is how the type of the reservoir that we are studying or are modeling, which is mainly reservoir studies. But this data is mandatory for us to know how to do our sensitivity for the well modeling. Let's say if we have some gas in solution drive or gravity segregation or something, we might expect some depletion in this reservoir pressure over time. So we need to do some sensitivity analysis upon the reservoir pressure to know how the well will perform in the future if the pressure decline. In other cases, if we have water drive mechanism, we might expect the influx of water. So we need to do some sensitivity analysis of water water percent into our well model to know at which percent of water the well will cease the flow. So to understand this concept of reservoir energy, it is mandatory for us to plan for our sensitivity in the well model during the well modeling. Another concept is the factors that affect oil production. This is some logical points. Is the amount of gas. In case of amount of gas in dissolved in the oil increase or decrease, this will decrease or increase the pressure losses during flowing the liquid up inside the wellbore. So it will affect the oil production rate. The same idea for the water cut or water percent in the oil, for the reservoir fluid properties or reservoir rock properties, for the producing pipe size or the tubing size mainly. This some the concepts that affect the factors that affect oil production. This is mainly our production system. Production system consists of the reservoir. The reservoir is the productive capacity and dynamic production characteristic over the life of the development. This is our reserve that we produce from it. Going to the well bore is the production interval in which the fluids come up. This also usually get this side using casing. So we had the well bore with mainly casing. Also, the production tube or completion string is we use to produce the fluids, usually to produce the fluid inside the production tube, in order not to affect our casing, not to damage our casing, whether this we have some corrosives, and to keep the well integrity for the system, the production system. Going up to the wellhead, Christmas tree, flow lines, all of this going till the treatment facilities. In order to be a production technologist, we need to analyze each part, each division of this production system, and when we have where we have our production losses or pressure losses. The concept of production technology. This is the first session in production technology. Production technology is a term composed of a lot of other disciplines, starting from well performance, in which is our session today is well performance, going to production enhancement and artificial lift, going to study of production problems, the well monitoring and diagnosis, workover operations, and how to do maintenance for failed wells, stimulation jobs in order to restore the productivity of our reservoir, surface processing, and well completion. This is the disciplines or that uh, summarize the term of production technology. So the role of production technologist is achieving optimum performance from the production system. In studying these terms, to achieve this, we need to understand the physical and chemical characteristic of the fluid. That's why we started with fluid properties. Also, we need to understand the engineering systems that will be utilized. Engineering systems means the artificial lift system, whether we use or not, the production tubing, any system, treatment facilities, any system that we will use to produce this oil. This is a summary of what is production technology. Uh, we already explained the term of full of production system. So at first we need to understand the well performance. The well performance, the productivity of the system depend on the pressure losses occur in several areas of the production system. So we had pressure losses in reservoir, we had pressure losses in well bore, we had pressure losses in tubing string, we had pressure losses in the choke and in the flow line, and we had pressure losses in the separator itself. So we need to study and analyze these pressure losses in order to understand the well performance. Okay, the liquid itself that we produce we know that it contain gas, highly compressible gas at elevated pressure and temperature that store within itself energy of compression. So sometimes this energy is not sufficient to lift the liquid from the reservoir to the surface, in which we need some sort of artificial lift. Uh, Beginning with to analyze this well performance, the first concept is inflow performance relationship. Inflow performance relationship is the pressure drop that occur from the reservoir till reaching the BWF or bottom hole flowing pressure is the point in front of reservoir. So in order for the fluid to come up from the reservoir to reach the well bore, there is some delta pressure or pressure difference that we name it drawdown that force the liquid to come from the reservoir to the well bore. The relationships that which control this amount of liquid is called inflow performance relationship. Also, another relationship that is important to us is the vertical rift performance relationship, which control the amount of liquids that come up from the point in front of the reservoir till the surface. So the other relationship is vertical lift performance relationship. Sometimes we name it tubing performance relationship. The same idea that we have two different relationships. We need to understand basically to know the well performance. Okay, the concept of well completion is the process that we install the production tubing that will control how the fluids will come up into the surface. So in order to do a well completion efficiently, we need to understand the fluids that will be used to the reservoir fluids. We need to understand how the fluids will enter the well bore from the formation. This means that whether our reservoir is very tight or it is the permeability is good, the productivity of the reservoir itself is good. We need to design the completion itself, how to make our completion strength or our tubing is safe to produce this fluids. Safety is a major factor here to how to provide capability to allow the fluid to the surface safely with minimal loss in pressure. So we know that as long as fluids come up to the surface, there is some pressure losses happen. So we need to reduce this pressure loss as much as possible, and we need to produce this oil or this liquid safely into till reaching the treatment facilities. Also, some other functions that might be considered during the well completion. However, we will produce from one interval or several intervals. However, we need to simulate if an advanced system let's say we have some sand production and we need to control this sand. We need to install sand. Sorry. We need to install sand control systems. So we need to simulate how much pressure losses that will happen inside this sand control. That's why there is some components that might be installed inside the well completion that to control the safety and control the fluids going up into from the well bore. Also, we need to consider sometimes the corrosion itself to select to choose the materials suitable for our fluids. Okay, another concept of production technology is production problems. We had a lot of production problems that might occur during this production system operation. Major problems like incompatibility. Incompatibility means that if we have completion fluids incompatible with the formation fluids or formation water, we might have some plugging of scale. We might have mechanical collapse of formation in some cases. We might have corrosion from H2S or CO2 or mixed corrosion from both components. If this might happen, we need to consider these production problems during the production technology or during the well performance operation. Also, we need to consider also processing problems. However, we have some sort of forms of scale of 4 point, let's say. So this all the problems that might occur during production operation. Workover, we already introduced to the concept of workover. Workover is operations that is used to maintain or repair the well completion. So if we have some sort of problems happened inside the well completion or a problems that prevent us from reducing the fluids, we usually do a remedial job or workover jobs. So we need to plan this corrective action clearly to first identify the problem, identify the source of this problem, plan for the corrective action, assess the probability that this could succeed or not, identify the required resources or whether this is possible to mitigate this problem or not. So the workover phase is the remedial job that occur for the well to help solve the associated production problems. Artificial lift, we use artificial lift if some cases the production rate from the wells or the reservoir is not able to lift the fluids up to the surface. So the energy inside the reservoir is not sufficient to lift the liquid to the surface, or in some cases it lifts the liquid to the surface, but at not economic rate. Let's say we have a well, but the energy in this well can produce up to 50 barrels, but 50 is not economic for us, so we need to produce more. So sometimes we need to install artificial lift system to get an economic rate, or to even produce the well in cases the well can't produce. Artificial lift can be categorized into major disciplines or two major categories, either to install a gas lift. Gas lift basically to inject gases inside the stream of fluids to reduce the pressure losses that happen during the flowing up inside the well bore. This is basically the gas lift. So the gas lift, we need to reduce the hydrostatic head. We need to reduce the pressure losses that occur during the VLP, during the flowing up to the surface through a gas lift valve. This is gas lift technology is a big area of study in terms of design of installation of troubleshooting and so on. But basically, this is the idea behind it. Uh, Other way is to install a pump, whatever the type of the pump, but the pump basically provides additional energy for the liquid to overcome these pressure losses while flowing up to the surface. So whether we install electric pump, whether we install hydraulic powered pump, whenever we install road pump, so any pump is to provide the energy required to overcome the pressure losses from the fluids during flowing up to the surface. Each artificial lift system has a selection criteria or a preferred operating envelope. So the pumps don't like sand, so we need to consider we have to consider gas lift. Maybe by pump also don't like gas, so in case of high gas, we might consider gas lift. Sometimes we need to produce a lot of rate, so we might consider electric pump. So this is mainly the selection criteria or the operating envelope for each system by many factors like the production rate, GOR, gravity, a lot of factors that control how to select optimum artificial lift system. Service processing is also a pillar in production technology to effectively separate oil, gas, water as a surface. So we need to exclude water and remove this material, other produced material such as sand. Also, we need to monitor and adjust chemical properties of the fluids. We need to dispose oil and gas per pipeline, and we need to study these pressure losses that might occur during this process. We need to prepare or re-inject necessary fluids such as gas or water for pressure maintenance. Pressure maintenance means we need to maintain the reservoir pressure. We need to overcome the problem of depletion inside our reservoir. This is the term of surface processing. Going up into the nodal analysis, our topic today. So all previous terms is introduction to understand the concept. Sorry if you have some questions here, but we can keep the question at the end of the session. Okay, going on into the nodal analysis. Nodal analysis is our session today is to do nodal analysis to know exactly how to the well performance and how to predict or to plan for the production mechanism for the well using software which is Prosper. But we need to understand two concepts first. Uh, okay, we already introduced to the inflow performance. Inflow performance means that the relationship that controls the pressure losses that happen from the reservoir into the well bore, into the point in front of the well bore. It is a measure of capability of the reservoir to flow fluids to the well bore. So depends on the mainly the reservoir properties. Let's say formation permeability. How is this rock grains, whether it is fine grains or coarse, or whether we have high permeability or low permeability, whether we have tightness or no. Also depend on skin, whether we have formation damage that occurred in the perforation or in the reservoir that might prevent us. Also, depend on the reservoir pressure itself. So it is a relationship that it's controlled by drawdown. Drawdown means the pressure difference between the reservoir and the pressure in front of the perforation. So this pressure difference will basically depend on the reservoir pressure, the drainage or the reservoir the reserves that we are producing from. Also, the other factors like formation volume factor or oil viscosity, this all that controls the flow performance relationship. Darcy began our the analysis of inflow performance relationships. That is the all factor of Darcy, because we usually don't have all these numbers. So we can summarize this in a one figure is BI. BI is productivity index that is relevant to Darcy. There's a lot of factors, including permeability, vertical height of the perforation, including viscosity, formation volume factor, a lot of factors can. So we can summarize all these factors because we not all times that we have this data with us, so we can do like a well test to get this all this factor in one figure, which is a probability index. Information relationship mainly is we have some major factors that is might be misleading for some situation like skin or formation height. So sometimes we had permeability reduction on the wall due to infiltrate of drilling fluids of muds that will prevent the liquids come from the reservoir. Formation height is we need to understand that it is the sum of perpendicular height of net permeable sand bodies contributing to the production. So this is a factor that is controls the inflow performance relationship. We have several models, all of them in Prosper, but each model is selection of each model depend on our understanding of which reservoir we are studying. So that's why we introduce the different drive mechanism of reservoir. Let's say whether it is under saturated reservoir or saturated reservoir, whether it is gas reservoir or oil reservoir mainly, uh, based on the value of GR. However, the drive mechanism is water drive or depletion drive. So we have different model for different reservoirs. So the selection depends on our understanding of the reservoir itself. This is basically the relationship. It will be like that in if we have under a saturated reservoir in which the reservoir pressure is more than the bubble point pressure. It will be a straight line with starting from the reservoir pressure on the vertical axis, going to the absolute open flow on the horizontal axis. We will study this in Prosper mainly. How to do the equation, mainly we usually do some sort of testing, and we do some matching between the testing and the model to get the best IBR model for our system. But mainly the BI equation is widely used to describe single phase because the reservoir pressure is more than bubble pressure, so we don't have gases, we don't have oil. This is the basic model that we will use today, let's say. Also, productivity index is a factor that controls the capacity of the reservoir to flow liquids into the well bore in bar per day per unit difference in pressure, per unit of pressure difference between the reservoir and the bottom hole flowing pressure. Another model is saturated reservoir, in which the reservoir pressure is below the bubble point pressure, below the bubble point pressure. So we had a different model that is developed by another model which is named by Vogel. Vogel describes a saturated flow performance relationship of saturated reservoir at below bubble point pressure. So in some cases we have dissolved gas drive reservoirs. Again, understanding of our reservoir will control the selection of IBR model inside Prosper. This is the Vogel equation and how to use it to draw the ion flow performance relationship. In other cases, we can say undersaturated reservoirs, but at some time we can reach the point that reservoir pressure become below the bubble point pressure. In these cases, we have this hybrid model in which the upper part is basically the IBR model, the lower part is going to the Vogel model. We call it composite model. So this model is better describes that reservoir that can reach the situation of saturated reservoirs, or we can we in sometimes we need to produce fluids from reservoir that we can reach the pressure below the bubble point pressure. So the bottom hole flowing pressure reach point below the bubble point pressure. So we might have some gases at the production, and we might reach the situation of saturated reservoir. The other relationship is outflow performance relationship that that determines the pressure losses inside the tubing itself up to the treatment facilities. So in both relationships will control how much rate that this well can produce, or whether it will produce naturally or not. Outflow performance relationship or vertical lift performance relationship will depend on three parameters or three factors, which is hydrostatic and friction and acceleration. But basically, the hydrostatic is the major concept that we need to consider in vertical flow. So in horizontal flow, we are concerned with friction. So if whether we are simulating or do modeling for flow lines or flow surface network, we considering the friction pressure losses component. But in our case of vertical flow inside the tubing, we are concerned with the hydrostatic component or the pressure loss component that will make the total pressure loss inside the wellbore. So that's why we need to understand the flow regime or the flow direction to understand the outflow performance relationship. Uh, in order to simplify the relationship, we can make it into three components. That the tubing head pressure, this is the pressure required as a surface for the treatment facilities to operate. So in some cases, here we have separator, but this separator need a minimum level of pressure to operate efficiently. Maybe we have a manifold. A manifold is a gathering point for many wells. This manifold requires a point of pressure from this well to operate. So if the fluids come up with a pressure below this point, the well might not produce efficiently. So the first component is tubing head pressure. Second component is the gravity component. Third component is the friction. Second component is hydrostatic pressure. That's why we introduce the concept of pressure at depths at the first of slides. So outflow performance relationship will overcome these three components: tubing head pressure, gravity component, and tubing friction. So we understand the different relationships and control the fluids from the well. This is the fundamentals of well performance: outflow and inflow. So inflow is all flow from the reservoir to the well bore. Outflow is all flow from the well bore up to the tubing to the surface facilities. Inflow is controlled by reservoir process, properties. Outflow is controlled by production strength, surface separator pressure, fluid type, and composition. In order for the well to operate, inflow and outflow must be equal. This is the point of nodal analysis. So here we differentiate between different drive mechanism and different IBR model for each one. Here we differentiate between different vertical lift performance relationships based on tubing size, or based on the gas liquid ratio, the amount of gas inside this liquid. So that's why we need to understand the point at which the well will produce. The point at which is the intersection point at which the inflow equals the outflow. This is the point at which the well will flow efficiently. Also, we need to understand inside the nodal analysis the concept of the optimum rate. Not always the maximum rate is the most the is good for us. We need to understand the optimum rate. The optimum rate in some cases like this one, if we have gas injection, is a point at which is if we increase the gas injection, we might reach the point that the rate will decline. But we need to reach to operate the well at optimum rate, at which is the amount of gas is optimum for the liquid to be lifted. Not we reach a point of circulation for this gas. So this is the point of analysis, is to have to how to reach the optimum rate of production, not the maximum rate. This is how draw the vertical lift performance relationship. Usually, the vertical lift performance relationship in Prosper is driven by many models or many correlations, but basically it is a component of two components of friction and hydrostatic. In case of we increase the rate too much, the component of the friction component will increase too much. That's why the vertical lift, the outflow will increase. That's why here we don't need to increase the point of gas injection. We don't need to increase the friction component. Factors that affect outflow performance is, we said before, the fluid characteristics, the back pressure, because the component of tubing head pressure is major for us, pipe roughness to control the friction, fluid velocity also for the friction, vertical depth for the hydrostatic pressure, well deviation also for the hydrostatic pressure, because the pressure depth is done by vertical height. Also the flow rate. Flow rate will control a lot of factors for the outflow performance relationship. Here we have what is meant by pressure gradient. Pressure gradient we will see inside Prosper, that how much losses occur during flowing up for the fluids, for our fluids, to the surface. So in case of this curve reaches the surface with a pressure, so the well can produce naturally. And in other cases, this pressure gradient will not reach the surface with the pressure. That's why we need to install. That's where we need to install artificial lift. This is how outflow or pressure gradient relationship or pressure gradient line will be changed based on changing the parameter. So if we have higher rates in first graph, we will have more pressure losses due to friction, due to many terms. Also, a smaller tubing size mainly will have more pressure losses due to the increase of velocity of the fluids going up. Higher surface pressure also, if we have higher surface pressure, we need more pressure from the bottom hole flowing pressure to lift this liquid to the surface. Again, high water cut will increase the pressure losses. Lower API, which mean heavier oil or more dense oil, will make higher pressure losses going to the surface. Lower GOR, going to more dense oil or heavier oil, will also give us more pressure losses. So this is the major variable affecting the pressure gradient curve. We explained this before. This is how the rate will control the pressure losses inside the well bore. So the inflow performance relationship, if we draw this rate against the bottom hole flowing pressure, we can see the optimum rate. That's why we can. That's where we can get the optimum rate. So the procedure we will do in Prosper today is to analyze the performance, design the inflow, design the outflow, try to reach the point of intersection, whether it will happen or not. This is the point at which the well can produce naturally. So this is the procedure that we will do during the well performance. We need to reach the solution point, or we need to check whether we will have a solution point, or we will need to give the fluids additional energy to reach this solution point. So this is the sensitivity available inside Prosper: sensitivity for the inflow, sensitivity for the outflow. So we can do sensitivity on productivity index, because as we said before, this figure is not well known during all times, and we usually take it from offset data. We can do sensitivity on all terms of Darcy equation. For outflow, we can do sensitivity for the tubing size, for the water cut, for the GOR, for any additional accessory that might produce pressure losses. And also Prosper can give us opportunity to do sensitivity in both types. So we can do sensitivity, several sensitivities on inflow or outflow to understand each case how much rate can get on the surface. This is overall system performance. Again, this is overall system performance. However, the impact of stimulation, so we can understand whether the doing stimulation or doing acid job or frag job is beneficial for us, or how much gain that we can get by doing this sort of stimulation. Sometimes we need to understand how much gain that we can reach by only reducing the tubing pressure or wellhead pressure. So in case of having a manifold with high pressure, if we have a solution to reduce this pressure, we can evaluate how much gain that I can get from my well. This is an production optimization action or methodology that is mandatory for any production technologist. Also, this is for the design of coil completion design. We can evaluate the tubing selection and how much production or solution points that we can reach, whether we select different types of tubing. Here we explained before that we have two different types of artificial lift method, which mainly the pumping, whether it is electric or rod or road pump or hydraulic pump or gas lift. This is the different types of artificial lift methods, and we already said that based on different type we can have different vertical lift performance relationship. So we can evaluate the effectiveness or the effectiveness of each system on our well, or how much rate we can get by selecting, let's say, either operating the well naturally, or using gas lift, or using SV for this example. So we can get incremental rate gain, or evaluate the incremental rate gain by selecting the artificial lift system. Also, we can know the optimum gas lift method, or and we can also draw the sensitivity based on the whether we have stimulation or we don't do stimulation. So a lot of sensitivity can be done for the well performance relationship, to design the well, with our best case to reach the optimum rate of production. So we have a lot of challenge question to pick the best artificial lift method, or keep the well flowing naturally. This is challenge question that will give us the selection criteria of the artificial lift method. So the operating condition, as we said before, the operating envelope will control the selection of the artificial lift system. Whether we have high volume, we need to go for ESP pump, electric pump. Whether we have high GR, we need to go for gas lift. This is a guidance, not a mandatory, but a guidance for us to pick the best artificial lift system for our well. We complete our introduction for the production technology. I hope to summarize that the major or the main definitions that we need to understand before going to the well model. We will use Prosper. Prosper is a well-known and of multi-phase well and pipeline nodal analysis. Prosper is old program that is used inside IBM, or integrated production management system, with other softwares to do digital oil field system. Prosper is used for inflow performance relationship, for outflow performance relationship, to do the nodal analysis, to understand the well and pipeline model, to simulate steam wells, whether we have sagged system or steam assisted gravity system. Flow assurance problem, whether we have some scale or some flow assurance problems that might occur during our operation surface facility. So a lot of things that we can do with Prosper, but we'll start with basic well model, and we'll extend this model with time. I hope I could cover the introduction, and now we can go to the Prosper, but I can take any questions now, whether there is some questions before going to the software. For first question, can we download Prosper for free? Yes, as long as it can be used for only not for commercial use for the company. If you have some study or something, there is some versions of Prosper available online, but it is cracked, but it is not recommended for professional work. But yet, yes, it's available. Thanks, Shahab. The primary objective nodal analysis is to reach the optimum operation envelope of production. So we need to ask ourselves that challenge questions. How much rate I need to produce this well economically? We can say that sometimes we had natural flowing wells, but it can produce naturally with 100 barrel. However, is this 100 is sufficient for me economically to produce to develop this field or not? This question can be answered by nodal analysis. Sometimes we need nodal analysis to overcome operational problems. So let's say I need to design an ESP pump to overcome a wellhead pressure, or a manifold pressure. So for the objective nodal analysis, a lot of objectives. We need to evaluate how much loss or gain I can reach by installing stimulation or not. The benefit of using nodal analysis to evaluate the impact of well bore friction. Yes, we understand that increasing the rate will increase the velocity, will increase the friction component. So nodal analysis can give me the answer of whether how much loss or gain by the well bore friction production rate. In which phase of production we can use Prosper? We can use Prosper for the initial modeling. We can use Prosper for the optimization. So, and sometimes we need to design the well completion before it is installed. So we use Prosper, and sometimes we had oil running, and we need Prosper to optimize the operation, to optimize the rate itself. Yes, for sure. Especially WebSim for production analysis. For sure, WebSim is another software that is used for well performance and production analysis. Yes, WebSim can be used for sure. The presentation, okay. Yes. The keynotes that we analyze, will analyze the inflow performance relationship. We will analyze the vertical lift performance relationships. We will analyze the solution point. So I think I answered all the questions here. Going to what's the procedure? The fluid will enter in the from information. I didn't understand the question. Inflow performance relationship is the relationship that will control how much rate I can get during the drawdown process, during the pressure difference between the reservoir pressure and the bottom hole fluid pressure. This is the IBR. Enough question for now. For the technical part, we can go to the practical part. Okay, we will analyze the this is how Prosper will start. We have here well schematic. We have here the some well reference or summary for the well we're producing. Going, this is section 1, section 2. Section 3 is section 2 is BVT, section 3 IBR, section 4 is equipment. Then we reach our analysis summary. So we can just double click on the option summary. It will give us this screen where we do a basic data or what is the basic reference data that we'll use during modeling. So we have here oil and water, black oil, or we will model gas well. We have separate single phase separator. We have immersion or not. This is basically the main reference, the main info of the well model. Whether the well will flow from tubing or from the casing, because sometimes we can produce from casing. This is a production well or water injection well, for example. So we can simulate or do well performance or modeling for different types of well. Whether we will install artificial lift from the start, or we will analyze the well naturally, then we go to the different types of artificial lift. Here is the user information, the companies, the fields, the location, the well name. Let's say it will X. The analyst is a date for the analysis. This is a good information that can be used for reference for us. Any comments that I need to remind me for server before executing. Okay, once I will pick this well, we will model black oil well. Black oil means that major production is oil, not gas well. It is an oil well, and we will evaluate whether will produce naturally or not. So no, so I will not change anything here. Just I will not pick any artificial lift method. I will use producer tubing flow. Once I say done, we have some changes here. some changes regarding the PVT, the IBR, the equipment data. So as long as I have these X's, so I need to complete my model to reach this analysis summary. So I will go to the PVT input data. Okay. As we said, Ariel, we need to understand the fluid properties. So I got with me some basic data. Uh, okay, this is my well. I hope you can see the sheet. Okay, this is I gather this data that I can use for my model. So let's say my pressure is 3,500. I will go here. The gas oil ratio is around 500. So okay, 500. Oil gravity, light oil. Gas gravity, 0.65. Water salinity, 200,000 ppm. I can check whether I have some H2S or CO2 components. I will make it one and let's say three. Okay, so this is the mandatory data required, and basically I got this data from the PVT report. Uh, Sometimes I have only this data in cases I got this data from an offset well. Sometimes I have a complete PVT report. So I will make this as in cases I have only the data or this data, but I didn't do any PVT matching. What is meant by PVT matching? I will open up here PVT matching in cases I have the complete PVT data report. Complete PVT data report. So I need to match the PVT report in order to pick the best correlation for me for the analysis of bubble point, for the analysis of formation volume factor, for the analysis of RS, for the analysis of viscosity, because these parameters is calculated by correlation, but I need to pick what is the best correlation for me for the analysis. So in cases I have, I need to have this data, I will get this report. Okay. Let's say I have this pressure. I get this data from the PVT report itself. Gas oil ratio here. Gas oil ratio.
Excuse me, Engineer Ahmed.
Sorry. Yes.
We can't see the window that you are copying from.
Okay. Sorry. This is a window. This is a PVT report that I received from the reservoir. It is a lot of data, but I am interested of summary of PVT analysis. But summary of PVT analysis mainly is if I get downhole sample, I do some flash calculation or differential calculation, reducing the pressure upon the sample, and evaluate the values of oil formation volume factor, gas oil ratio, viscosity to uh, to to guide Prosper which the best correlation model that is used for the calculating of viscosity, beta O, RS, and this to define or to pick the best correlation. This is a PVT matching. So some good or bad well model based on good or bad will matching. This is the point here. So, but in all in many cases we don't have the PVT report. But I propose that I have a complete data for the oil. I have a PVT analysis, complete PVT analysis for the whole sample. I have the well data is very accurate. So I need to do an accurate model for the well. So this is the report that I received from the lab, the PVT analysis report. The last points is the temperature and the bubble point. I need the temperature of analysis, the bubble point analysis. Temperature is 232 Fahrenheit, and bubble point here is the pressure at which this is the bubble point pressure 767. Here I do sorry. Here I can see which model is giving me the best values for the analysis to understand the best correlation method. Sorry, I the problem here. Until I reach that PVT is matched with our my data, and the software give me some guidance whether this is the best correlation I can choose based on these parameters to make the model more relevant to my actual fluid. So here I do a PVT matched. This is in case I have the PVT report, but in other cases I don't have the PVT report, so I don't need to do the PVT matching. But PVT matching is a crucial step in well modeling. Going to the IBR or inflow performance relationship, this is the reservoir model, but I need to understand my well. Here my well is reservoir pressure is 3,500 and the bubble point pressure is almost 600. So I have undersaturated. So I should pick either BI entry or a composite. Composite is the hybrid model that sometimes I could reach the point at which the bottom hole fluid pressure will go below the bubble point pressure. So for me, I will pick the composite model to understand to simulate in cases of points we in which we have this sorry this in which you have gases into the wellbore. Okay, in case I have a BI, I will pick the BI entry. Let's begin with BI initially, then going to the composite model. I will simulate that BI is 0.7. So BI mandatory item is the red items. So reservoir pressure is 355, reservoir temperature 232. Water cut, I will simulate with zero water cut at the beginning. And the BI entry here is the red point is 0.7 is the worst value. Calculate, done, done. So I have here the inflow performance relationship, and the Prosper guide me directly. The case is the well can produce or not, but I didn't reach the point of the equipment data. So here I have the draw the inflow performance relationship. I have draw the Prosper said to me that this well can produce naturally, but I didn't reach the point of sensitivity because I didn't do any equipment. Okay. Here I will start with giving the required equipment data for my model to do the other relationship is vertical lift performance relationship. So this requirement is needed for the vertical lift performance relationship. So the upper part, the PVT, the well data, the IBR model To draw the blue line is the IBR model. So the lower part draw the other relationship with this VLB. Okay, I will consider here is our data. Our well is perforation depth is 8,700 feet. And this is the point at which this pressure is taken. The tubing size begin selection is 3.5. I will evaluate this well is here. This well is vertical. Sometimes I had the gradient, the survey of the well bore, but this well is vertical. So I here I will type this. Let's say this is well bore. I have vertical well, so I have same depths in true vertical depths and measured depths because I have vertical well. So I completed the deficient survey. Surface equipment, I will include surface equipment in case I do a network modeling or in case I need to simulate or model the component, the horizontal component of the well. But I will keep it for now because this is not important for me. I need to evaluate the well, how much production rate can be reached with this condition downhole. For the downhole equipment is very important. I will begin with my casing, then my tubing to evaluate the well. Okay, let's say the casing is we said that it is 9,000. Sorry, because the zoom is preventing me to see the screen. Okay. Tubing, I will not reach the end of casing. I will not reach the perforation tips. I will assume that it will be 8,500. So basically, the well bore will reach 9,000. Perforation is at depth of 8,700. Tubing end is 8,500. Tubing inside diameter is 3.5. I can select the tubing here from tubing database. Prosper can give me guide what is the tubing that I should select to pick the nominal OD, the tubing weight, the nominal ID. So I can pick exactly what tubing I will use. But to make it simple for now, I will use 3.5 tubing. Here for the casing, casing is 7-inch casing. So a casing inside diameter, I can see here for the casing database, the casing OD 7-inch with weight of this one is inside diameter is 6.184. So this in the case of if I have just 7-inch casing. Also, if I have several accessories like SSV, like a choke, like a restriction, I can consider in download or comment. If I go this the here I have this errors that there is some missing data not complete because I inserted only the deviation surveys, downhole equipment only. I go to the sorry here retrieving first casing. Okay, geothermal gradient is the temperature at surface and measure depths. So at surface, let's say the temperature is 120 Fahrenheit. This is the surface temperature. Downhole temperature, we know that it is 202. Downhole temperature at 8,700. Heat transfer coefficients, we use it generally 8, but we can do some matching for this value, whether this value is accurate or not. But we need to keep it simple for now, so we'll use it. Heat transfer is 8 for now, then we'll match the correct value. Heat capacity we don't change, we keep the gauge data if we do some memory gauge survey. if we install mirror gauge and measure accurately the downhole pressure. Here we have some equipment error depths in downhole equipment deeper than the thermal gradient. Okay, we reach to the thermal gradient because here we don't reach the 9,000. Done, and we are all done. So surface equipment is not important for our model because this is important for the surface network modeling. Gauge data, you don't have gauge data, but we have the reservoir pressure. So we don't include gauge data, but this several diffusion surveys, the downhole equipment, the thermal gradient, heat capacity is the only important factor to get the vertical lift performance relationship. Okay. Let's say reach system evaluation. I will evaluate how much rate I can get based on my parameters. If I when my oil pressure is 500 psi, based on the data calculate input for the IBR for the VLB, I will do calculate and see what happens. So the model says that this well can produce with only 200, let's say 300 barrel of oil at zero water cut. طب let's say we need to do some sensitivity on the water cut. I need to do some cases of water cut beginning from 10 to 20, 30, 40. I need to do this analysis for all for different values of water cut to know which water cut the well will stop producing. Calculate for all show calculation step. I had all this equation. So at water cut 10, the well still producing with almost 200 barrel. At water cut 20, the well is still producing with less than 200. At 30, the well can't produce. So at a point between the water cut of 20 and 30, based on our input of data, the well can't produce naturally. This is the benefit of nodal analysis, as we said before. We need to understand how well will perform based on several parameters. I can see here sensitivity plots for several water cut. I can see the system plots all cases together. So I can draw the liquid rate and VLB IBR for all cases. Okay. So this is a graph for all our cases, beginning from 10% of water cut, 20% of water cut, 30, 40, and going on. So at a point of between 20 and 30, our well can't produce. Also here we can see that IBR model have some deviation with different water cuts because of the more water cut will less water cut will give us more losses in the IBR curve itself. But we are interested here with the point of intersection, as we said before, the solution point of the nodal analysis. So this will we can decide now whether we will install this well as naturally. Is this economic for us to install this well for naturally or not, or we need to consider an artificial lift method to produce this well? For sure, for economic point of view, I consider this will have a water influx because this is a water drive well. So I expecting a water will come up very soon. So I will install by Prosper an artificial lift method. So here I don't have an artificial lift. I should come back to the options here to change my artificial lift method from none to I will pick electric submersible pump because I need to produce high rate with high water cut. Model produced oil only. Okay, done. So I have here another section for the ASP. But before I going to the ASP, I need to design the ASP itself. So I will go to design for electrical submersible pump. Prosper can give me the aid of design itself. But here the design of ASP have some errors. This is a good point for Prosper because Prosper guide me where the error after using ASP. ASP is keen about the float velocity around the tubing because this float velocity will control the cooling of the motor itself. So some missing data here in the downhole document is the outside the for the tubing outside diameter and tubing outside diameter for us for the 3.5 tubing. Let's say this is 3.5 tubing and outside and the inside 2.992 3.5 tubing. Okay, done. Let's see whether he will do the design or not. Okay, he is now can do this design. To do the design of ESP, I will not go in detail for the design of ESP, but mainly this some required information. How much how much pump depths? Oh, to install the ESP, we know that the reservoir depth is here is top of berth depth is 8,700. So I will pick some depths above this depth. I will make it 8,500. I'll operate at 50 hertz. Considering that I don't have a VSD. Maximum body, we have 7-inch casing, so we could say it is 5.4 length of cable for the analysis. Okay, and 5 gas separator efficiency. Whether there is install a gas separator or not for this SP, I will consider not to install gas separator. I will make it natural separation only. Design rate, I need how much rate I need. Let's say I need 1,000 or this will can produce more 1,500. Water cut, I will keep it 90. I need to produce 90%. GR tube head pressure 500. Power safety margin, yeah, let's say 10. Pump wheel factor is 0.1. Calculate pump duty. So I need here some required TDH, the total dynamic head required to know how much stages I will use. So head required is 7,000. Power required is almost 100 horsepower. I can keep big one pump. Let's say this pump. This is best for us because it is produced from 1,000 to 6,000. I need 100 of horsepower. I will get this one. This is good for me. Size 4 is good also. So he calculated here the number of stages. How much stages I need to produce this 7,000 feet of lift of total dynamic head. Basically, to do an ESP design, I need to calculate some value called TDH, total dynamic head. Total dynamic head is the pressure, the additional energy required by the ESP to be given to the liquid in order to overcome the pressure losses and reach the surface with this wellhead pressure. So I input this data. He calculates the total dynamic head based on the selection of the pump. He calculates the number of stages and a lot of other things. Okay, done. I am here done with my equipment. So here I can see that the completion string have been revised considering the ESP, and I can recalculate our cases with different water cuts at 50 hertz at this number of stages of the ESP, and all the cases as seen before. So I will not change anything. I will recalculate all these stages, all these cases. And you see the system plot all cases together. Okay, done. Sorry. Here I could reach with this 90% of water cut the value of my target rate, which is 1,500 barrel of oil at 90% of water cut. Before installing the SP, I couldn't reach any production at a point of water cut between 20 and 30%. So here I can calculate the VLB, and I do the nodal analysis for all cases at different water cuts. I can see the sensitivity plot starting from these several water cuts and the pressure inside. I can change this pressure to the rate here. Done. Sorry, it's not working fine because it's still making analysis. Okay. Also, I can make change this to another parameters of any other parameter, not just water cut. Let's say I need to do any analysis or sensitivity analysis. For example, frequency, whether I will work with 40 or 50 frequency or 60 hertz frequency. Done and recalculate. So at this 90% of at 0% of water cut and 40 hertz, I can produce this amount of rate. And at this frequency, I can produce this amount of rate, and 60 frequency, I can produce amount of speed. But here I couldn't produce because the reservoir is not giving me enough liquid to produce this well. But basically, I can do any sensitivity. This is the power of nodal analysis. I can do any sensitivity based on water cut, based on operating frequency, based on whatever the variable. Let's say I will recalculate of 90 hertz and change the cases, remove the 60 hertz, 40 and 50 only, and recalculate. Just very simple as it is. 40 hertz, I can produce almost 600 barrels. 50 hertz, I can produce 1,500, which is the target rate for my design at this GOR, at this tube wellhead pressure, at this water cut. This is the power of Brusbar. Brusbar can give me hundred of or thousand of scenarios of reducing my well. Based, as I said before, the crucial point or the most important point for the analysis is VVT matching. If I have a good VVT, I will have an easy well model. Also, I need to be more accurate inside the details of the data, whether I will install any accessories or not, whether I will install backer, subsurface, choke, restrictions. I can model anything. I can model any pressure losses inside the well bore. I can do any sensitivity based on water cut, based on the wellhead pressure, based on the operating frequency, based on the number of stages itself. I can model based on the selection of the pump, of the ESP pump, whether this pump is efficient or will cover my all sensitivities, or the pump range is limited. And in some cases, I will not operate outside the recommended operating range of the pump. This is the power of the Brusbar. Brusbar can give me these insights more easily. This is a basic introduction for the well performance. For sure, Brusbar have a lot of models, a lot of different models, different scenarios, different sensitivity, and I can almost model everything inside the Brusbar. Now I'm done. I can take any question required. I'm sorry that it take more than 1 hour, but
No, it's
anyway, if there is
okay.
any question, any
Thank you,
questions
Engineer
required.
Ahmed. Thank you,
Thank
Engineer
you.
Ahmed, for this wonderful session. Before we jump into the Q&A section, we should have a break for 5 minutes to fill this feedback survey form that I will send in the chat box right now. So let's back in 3 minutes, okay, to receive your questions. So let's have your questions. If you have any question, please type it in the chat box so that Engineer Ahmed could answer it.
Uh, okay, Engineer Shahab, I will share the link to on the group and to for you to how to install it. It is an easy installation software for sure. Okay, Engineer Hadi, why don't you use a sound control? For sure, Prosper can simulate the center control system and how much pressure losses could occur and how much efficiency efficiency of the sound control system. But here I will not go into the sound control mechanism because I this is from experience for sure because I will know whether this will in this field will have in the future sound problems or not. Which software is the most suitable? Here I don't compare between the softwares. So there is PipeSim, there is Prosper, a lot of software in the market. Each one has its pros and cons. For me, I see that Prosper is the most suitable one, but it is not a preferable solution. PipeSim also is a very efficient, but Prosper have more models than PipeSim in some cases. Let's say for the steam wells, PipeSim don't have it till now. PipeSim have also some advanced models like dual completion for now. Also the integration with Python. So each software has its own advantages. It's your preference whether to use PipeSim or Prosper or any other software. But this is not preference for anyone. Okay, surface comment is important if I want to evaluate the pressure losses after the wellhead. In if I have a network model, if I need to evaluate how much pressure losses that will happen during the flow line between the wellhead and the treatment facility. This is where I need to fill the surface comment information. But in my model, I didn't need it in the nodal analysis itself for the well performance. I just need to know what the well perform at different water cut, whether it is a mandatory TNS or artificial lift system or not. But surface comment is important if I will include this well model inside a network model. Okay, we can get the data. Yes, for sure. I can send the data. We have all the data when you use the Bruce My Future. We must. Yes, sometimes a lot of time we need to do some assumption and calculation, and it is based on the experience from the field itself. So as I said before, in all times we don't have all the data. We don't have BVT reports, complete BVT report. Sometimes we take data from by analogy. If I have an offset well with a very near, and I can take its data to build my model in this well. Sometimes I do some assumption, yes, for sure. And sometimes I have all the data, but in our case, fortunately, we have all the data for the model. But yes, and sometimes, and many times, we do some assumptions. Challenges arise depend on the pressure losses. Basically, let's say if I have a high gas, it will do gas interference to the pump system that I installed. If I have more gases, the system will not operate at all. So yes, transition between different flow regimes will do some problems in the completion equipment and lifting systems. Yes, for sure. As I said before, we have different IBR model, we have different VLB models. Prosper can give the opportunity to do some BVT. Sorry, as we did BVT matching, we can do VLB matching. We can take the help from Prosper to pick the most suitable VLB model for us. For the IBR selection, it is based on what we have in data. Whether this well is undersaturated or saturated, whether this well is oil or gas, based on the value of GOR, based on the case whether we have all requirement for the Darcy equation or we just have the BI values. So based on what we have on our hands, we can pick the IBR model. But VLB, Prosper can guide us which VLB is the best efficient VLB model for us. Yes, for sure. You can rewatch it on YouTube. For sure, Prosper can contribute to the optimization injection strategy because Prosper can model injection well, and I can change the fluid properties that is injected from water to any other fluids, and he can simulate what happened down at the node or at the surface. So yes, Prosper can contribute to the optimization of injection strategy for enhanced oil recovery projects. Which well schematic is better? A well schematic is not an optimization case. I didn't understand the question. Yes, as said, Prosper can give me the sensitivity whether to install ESP or use gas lift, for example. So he can do sensitivity on the selection of the equipment, not the completion schematic. The downhole equipment and surface equipment is controlled by the well bore. So I can use Prosper to pick what is the most suitable artificial lift system for me, or whether to pick which tubing size. So I can do sensitivities with tubing size, for example. So yes, you can do sensitivity on the equipment itself, not just the reservoir fluid properties, for sure.
So, do we have any more questions? Okay, I
Thank
think
you so much.
this is all for today. Thank you, Engineer Ahmed, again for this wonderful session, and thank you, OPA interns, for attending today's session. Thank you.
Thank you so much. Thank you all.